Today, if I stand up,
Please, yeah, Robert, present it if you wish. Yeah, no worries.
I'm not going to present some specific research work, but I'm going to talk about some overall things on fundamentals of holographic-based communication. It is more about applying holography in electromagnetic. And so, as long as you're going to work on radar systems, you can apply this holography on prototyping antenna for radar system as well. But you can apply holography theory to design leaky wave antenna, reflective antenna, and all these things can be a good candidate to be utilized in radar systems. So I think it's would be nice to talk about this structure, and as long as holographic-based structure, we end up with a kind of periodic structure, and I mean a geometry would be repeated in such kind of a structure. Sometimes maybe there might be some misunderstanding between holographic-based structures and arrays and MIMO systems. So I'm trying to just explain the differences between a holographic-based component, an array, and MIMO system. In all these three, we see geometries repeated. So, but there are some fundamental difference between these three. So to begin with, I'll start with origins of holography, which is rooted in optics. Generally, to come up with a portrait, we have two methods, photography and holography. We all know about photography. This is to illuminate an object by this camera lens and then read the reflected light ray. The reflected rays from different colors of the object will have different intensity. So the camera sensors will detect those intensity and will end up with a two-dimensional photo out of the structure. In this method, the phase of reflected wave will be lost because we just rely on the intensity of the reflected wave. This is the reason that we end up with a two-dimensional photo. In holography, we not only rely on the intensity of wave, but we record the phase information as well. We combine the phase information and intensity of the reflected rays to end up with a three-dimensional portrait of the object. To go a little bit deep through that, we can say that in general, holography is divided in two steps, recording and reconstruction. In recording process, this is the photo plate, which is going to be illuminated by a local light source, which can be a laser light. So we call it reference phase. So we have the photo plate, which is illuminated by reference phase, and this source will also impinge on the object, and these waves are going to reflect back to photoplate as well. So we have a reference to compare the reflected wave to that reference. So the phase information of this object can be extracted by comparing to this reference wave. And as long as let's say like that, in reality, we have two eyes, and our brain can detect the phase difference from the rays that comes to my mind from side position, and based on this phase difference, I can feel the depth of this spot. And also, the same thing will happen to me when I look at the object. So the sense of feeling for our eyes will be processed by the phase difference. This is also happening in array antenna as well. For array antenna, we also rely on the phase differences between elements. But here, when our eyes look at this object wave, it can fill the depth. So what we should do is to find a way to actually reproduce such kind of wave so that our eyes virtually feel that this photo has a three-dimensional aspects. So to do that, by comparing these reference wave and object wave, we end up with an interferogram by making a superposition of these two. We print out this interferogram here, and then again illuminate this. Right now we call it hologram. This photoplate, which has the layout of the interferogram, is called hologram, and then we illuminate the hologram by the source exactly similar to what we have used here during the recording process. So in this case, the mutual effect between this laser light source and the layout that we have printed will produce an object wave which is exactly similar to what's happening in the real scenario. So it is like that we have a virtual image on this side, and as long as our eyes looking at this object wave, it can feel the depth. So in this scenario, we just include the phase information inside this layout that we are printed in. For the hologram bag, when we look at them, we slightly try to change its angle so that at some specific angle we can feel the depth more visible. In this case, this is exactly the angle, the relative angle that our local lights would be exactly at the same angle that during the recording the manufacturer had used to build that hologram. So this is the reason that the sense of depth of these badges will be more visible at some specific angles. These are the, and we call this process as a reconstruction. So the hologram is divided in these two, recording and reconstruction is the final step of making the hologram. Considering these backgrounds on the holographic in optics, let's move on to the electromagnetic-based holograms. To start this concept, it is better to start with the leaky wave antenna, holographic-based leaky wave structures. And this is the basis of all other things. So I personally am a great fan of leaky wave structures. Let's keep this one as a reference, as a reminder at this side. And let's start with have a brief discussion on leaky wave antenna. You know, in general, we have two types of antenna: resonating antenna and traveling wave antenna. For resonating antenna, the size of antenna should be something around λ/2. So a resonance should be happening, and then this resonance will end up with radiation. In traveling wave antenna, you have a wave packet, and you are going to govern this wave packet in a way that this wave packet is usually enclosed by a guide. You know, it is inside a guide, it is attached to a guide. Then you need to reshape it, govern it, so that this wave packet inside the guide ends up with a radiation. Horn antenna is one example of this traveling wave antenna. You have a waveguide inside the waveguide. This is some wavefront, and then you start to open the waveguide at one end. So these waves will have the chance to be circular and push forward, so a radiation will happen. Leaky wave antenna is also a category of traveling wave antenna. You need to have a feed at one end. This is your guide. It can be waveguide, it can be dielectric as well. But you need to put a feeder at one end and preferably a matchload at the other end if it is a waveguide. If it is a dielectric slab, that one feeder would usually be enough. So surface wave or guided wave in general is happening in here. And by putting an aperture on this guide and governing the shape of the aperture, these guided waves will be engineered to be leaked out to the direction of interest. And by this mechanism, radiation will happen, and you end up with an antenna. What is the relevancy of leaky wave antenna and holography? This one was our concept in optics. When we want to jump to the electromagnetic scenario, then this photo plate here will be recasted by our dielectric slab. Assume that we have a dielectric slab and we are going to do everything that we have done on the holography theory on this dielectric slab. So we need a reference wave. We can assume that we have a point source at one end. So this point source will produce some surface wave on this slab. So this is our reference wave here because it is produced by our reference wave launcher. And here we also need to have an object wave. In leaky wave antenna, we define the object wave exactly to the direction that we are going to produce our beam. So assume that our leaky wave antenna is going to radiate towards some specific direction. We define a source at the infinite position, but at the same direction that we are interested. And we assume that that source is going to impinge on our slab, and we call it our object wave. So this is the effect of our point source, our reference wave on the slab. We also need to calculate the effect of that object wave on the slab. So in this case, we have both the effect of reference wave and object wave on the photo plate. And here we have both the effect of reference wave and also the object wave on the slab. This is the photo from the top side angle. So we make an interferogram from these two, and we end up with this pattern. So by making a superposition between what's happening here?
Touch screen.
Oh, sorry. Main, yeah?
Yeah, I've never seen that. Touch somewhere else. Touch else. Oh, it's a bit laggy. Yeah, maybe touch away and then it should disappear. Let's go on.
Okay, that's good. So a superposition between these two, we can come up with such kind of hologram. And then now let's move on to the reconstruction process. All these was our recording process. In reconstruction, we said that we need a source exactly similar to what we have defined during the recording. So we will use a surface wave launcher. This is a connector connected to the RF port. A surface wave launcher in here, and we need to have a layout as a hologram in here as well. So as a sampling in here as well. So the pale blue is our hologram. If we want to sample this pale blue, one method is to put some metal strips on the maximum of these shaped hologram. So as long as we have these metal strips here, and we have a surface wave launcher exactly similar to what we have defined here, when we excite the surface wave launcher, the leakage would be happening exactly to the direction that we defined our object wave in the recording process. So this is how we can end up with a leaky wave antenna based on the holography theory. And to be more clear about that, this is one prototype. The pattern is not similar to this pattern, but we have, but the concept is same. You know, we have a surface wave launcher in here, and we put some metal strips to sample the recorded hologram, so a leakage would be happening. In this case, as long as you just do the sampling at the maximum, you will lose the phase information between each metal strip. So this is not a very accurate method of sampling, but it can work. It can end up with it can construct a very high gain, because leaky wave antenna will always have a relatively high gain. Now let's move on to the holographic-based reflectors. Again, let's put these three as our reference here. Instead of having our reference wave launcher at one end, we can put our reference wave outside the structure. This is our slab, and we can put the feeder outside the slab. So the rest will be similar to that. We need to calculate the reference wave map on the slab, and then define an object wave, which is introduced in our constructed beam, and then calculate the interferogram and end up with the hologram. This is going to be a reflective metasurface, which will do the same thing that's happening in the conventional reflectors. In conventional reflectors, you have a feeder, and by shaping this reflector, you can actually reflect the initial wave by changing the phase. You're regulating the phase of the reflected wave by shaping this reflector, and then a constructive reflected beam would be happen. Here, as long as you have a two-dimensional structure, not a three-dimensional, instead of shaping the reflector, we are going to producing a specific pattern in here. So the same thing would happen. This pattern will manipulate the phase in a way that the reflected wave can be happening. And this is a kind of metasurface sampling. Metasurface these days is going to be a buzzword. And this is, these reference waves are related to the case that we put our launcher at one end. If you put it here, then the reference wave map would be something like that. Then this is the reference wave map. And then I have defined two object waves. This structure will be ends up with a dual beam structure, because you will have this flexibility to end up with multiple beam out of these structures. So I defined two object waves. The mapping of these two object waves would be something like that. Making an interferogram between these two ends up with this pattern. And now we are going to make a sampling for this pattern. In this case, I think we can. Yeah. In this case, this is our hologram, the pale blue. And to do the sampling, we put some metal strips on the maximum. Right now, this is our hologram. And to do the sampling by these metal strips for such kind of a rapid variation, so it is not going to be an accurate method. So we will use the metasurfaces. And in metasurfaces, we have usually tiny patches. The response, these patches are at the size of sub-wavelength, and we need to follow the Nyquist theorem. In Nyquist theorem, the sampling rate should be at least half of the variation of period of variation. So this is so in this case, if you want to go for an accurate sampling, the size of these scatterers should be at the scopes of lambda over by 5, lambda over by 6. So they are much smaller than in conventional phasor, the size are lambda over by 2 because they are resonating a structure. But here, these patches are not going to resonate or anything. These are just a sample, and the response of each patch, if you change the size of each patch, the response of them would be different. For example, tiny patches would end up with this bar is actually surface impedance. These are not phase information. You can map the phase information to surface impedance because surface impedance is E over H. So you can find a relevancy between phase information and that. Here, I've recorded the surface impedance. So tiny patches would be mapped to the higher impedances and larger patches for the lower impedances. So based on this rules, you can pixelate your structure so that the pattern of these patches are exactly following the pattern of our hologram. In this case, as long as the sampling is very tiny, you're not going to lose anything, any phase information that you have lost with the metal strip sampling method. And if you put the reference very far from the structure, this is not that much far, this is at the focal point or something. If you put the reference very far from the structure, then you'd end up with a reflecting surface, which is these days called RIS, reconfigurable intelligent surfaces. You know, the concept would be somehow similar to that. And here, instead of changing, this is our unit cell, this is those tiny patches scattered. Instead of changing the size of this scatterer, we put a varactor there, and by changing the state of varactor there, it is as light as we physically change the size of patches. So changing the states of varactor there will artificially change the electromagnetic size of the structure, so you can have reconfigurability in the structure. Now let's move on to the area antenna and MIMO system. In area antenna, this is the fundamental formula of area antenna. Pattern factor is equal to element factor and times by area factor. It means that our element factors will have a specific, we should have a specific character. In metasurfaces, those tiny patches are just for sampling. But in here, you need to design it, you need to adjust the size so that the resonance happens. And for each patches, you need a separate port to make the radiation. And then when you put all these elements together, this lattice will define your area factor. And then for all these elements, all these ports can be connected together via a hybrid beamformer, via a network, something like that, which ends up with your single port. And by changing the phase, the relative phase between the elements, you can control the direction of a constructed beam in phase area antenna. And by changing the amplitude of each port, you can also control the sideward levels of the constructed beam. So in this case, each element has its own specific pattern, making an array out of them will end up with the radiated beam. And instead of having separated ports, you can just connect all ports together, and there's a corporate set array antenna instead of having multiple connectors. For MIMO systems, you again have a number of elements, but here we call these elements embedded elements. In array antenna, we call them element factor because we need the mutual coupling between elements and we are going to govern this mutual coupling to make this constructed pattern factor. But in here, we prefer to have some elements which are not related to each other. Each element should work on its own. So the corresponding mutual coupling in this case would be low, and the correlation between these elements would also be low. So in this case, as I said, each element has its own separate ports. So the constructed pattern would usually something like that. You have 4 elements, 4 very non-related pattern would be shapes. This is the spatial diversity applied for MIMO systems. You can also have a pattern diversity. This is a Rotman lens, and you have several ports. If you excite each port, the constructed beam would be inclined to a specific direction. So each direction will call a specific port. And you can excite all ports all together to end up with multiple beams, but again, each beam is related to one single port. In this case, in array antenna, your beam is related to all ports are going to combine with each other, and you will not have such kind of diversity that you have here in MIMO systems. So in MIMO system, the design of embedded element is something important, and the lattice of this element is also should be designed properly in a way that the mutual coupling between elements reduce appropriately. To wrap it up, to compare these two together, in array antenna and metasurfaces and MIMO system also, in all these 3 structures, you're going to see a repeating geometry. This structure is based on resonating antenna. So each element has its own character. You need the mutual coupling between them, and the story is quite different. But in metasurfaces, these elements are just to sample some induced electromagnetic phase. In this case, you don't have several ports of the structure. You have a port. This port induces a surface wave on the structure, and then by having these patches, you're just sampling the induced electromagnetic waves on the structure in a way that you would like. So we have a surface wave radiative beam, and we have a resonating beam in here, and MIMO system has also a different story. And yeah, I think this is all from my side, and this is just for a brainstorming. I have not put any specific here. Thank you. Thank you.